finally it's afternoon on Friday, so now we will have 2 hours of Reimundo, who will continue to tell us about Poisson vertex algebras and related stuff.
Thanks. Alright, so just let's recap a little bit what we did last time. We said that if you have Poisson algebras, everything generated in degree 0 and 1, freely generated in degree 0 and 1. Remember, we have all these conditions truncated if we want degree 0 and 1. Then we obtained geometric objects, some pair, essentially of a commutative algebra and a Lie algebra, which was a Lie algebra. And then we went one level up to Poisson vertex algebras. And we obtained something that was a commutative algebra and a Leibniz algebra. And then a derivation as part of the data, and a pairing from this guy to this guy, and this was a current orthogonal. So actually I should say I'm very happy that 3 names appeared in Damien's talk. So there are 3 names that are going to play a role in what I want to say. And they have a deep role, which is Courant is one of them. The other 2 are Mukai and Tachikawa. And actually the very same result that Damien presented is something that I will need next week in my talk. Well, okay, so at least I want to say how this fits into Damien's picture. And I'll restrict to some piece of this. I want to give examples of current orthogonality. This is where I stopped last time in the classical theory, and I want to give you examples of this. So the derivation, I said, produces a map. Oh, this was this, but this produces as a map from omega 1 into E, and the action of E by derivations on O gives us a map like this. And if this fits into a short exact sequence, this is called a current algebra. This is an exact, which was Pedram's observation, exact current algebras. So actually, my point of view on current algebras or Poisson vertex algebras is kind of transversal to this. My idea of what a current algebra is what I explained as the only example I gave of a current algebra is when the manifold was a point. And this was a Lie algebra with an invariant pairing. Which in the case of a Lie algebra, this was just a Lie algebra. So this is orthogonal to that. I mean, this is empty when the manifold is a point. But what is this? So this is, we can remember what were the axioms of these guys. So this E has a pairing into O, and now this pairing is non-degenerate. We're asking this time that this pairing is non-degenerate. And on top of this, we're asking this to be a short exact sequence. If you don't ask this, that's called a current algebra. So a current orthogonal algebra such that this pairing is non-degenerate, this is called a current algebra. And let me give you examples of this. The only one we care for these dots, or we care of these 2. So examples of current algebras. So the one that I already did is when OX is just my field K, there's no derivations, so obviously 0, and E is just a Lie algebra. And we have an invariant pairing. We have a symmetric pairing on G. And the second example is the standard current algebra that denotes A, and this is just Tx plus T star x with the Dorfman bracket remember I needed a bracket that satisfies the Leibniz rule. So I'll choose the Dorfman bracket, and of course I'll forget how this works. But luckily for us, we have Maxim here. So the Dorfman bracket is as follows. So I'll define this on generators. I don't want to write this in general. So I'll take the bracket of two vector fields, oops, x and y is just the Lie bracket. The bracket of a vector field with a differential form is just the Lie action of a vector field on the differential form. And the bracket of two differential forms is 0. Be very careful with this statement. Remember, my bracket is a Leibniz bracket, but it's not skew-symmetric. So the bracket of a differential form with a vector field is not minus this. So exercise what is the bracket of a differential form and a vector field. Remember, I gave you what was the failure of skew-symmetry was that this plus eta x should be the derivative of the pairing between x and eta. Okay, so I just solved the exercise. X eta plus eta x is just the derivative, which of course we only have one derivation, of this, of that function. Okay, so our bracket is not skew-symmetric. So that's a standard Courant algebra. This obviously fits in a sequence like this, so this is an exact Courant algebra. And if you're given, so I guess example number 3, if you're given some H plus, some 3 form that is closed, then you can play a little bit with this guy. You can change this guy, you can add to this term the contraction of your two fields with H, which is going to be a differential form. That's also going to satisfy the same axis. So if H, you have a 3 form that is closed, you can add to that first Lie bracket, which is the contraction of x and y with H.
Are you sure you wrote correct?
No, I'm not sure, but I don't. Why?
I don't think it's correct, but I don't remember.
Why? What is it wrong?
I don't remember.
No, I think
it looks. I mean, if you look, I mean, if you write a bracket of vector plus form, I mean, it looks like it's antisymmetric automatically.
What? No. This shows that it's not antisymmetric. Actually, I think it's correct. This statement is correct. This is the right bracket.
Oh, right. Yeah.
No, this is the right bracket.
This is right.
Yeah, this is correct. This is correct.
It's got to come forward.
Yeah, this is correct. But the whole point of this example is that notice that this is not our favorite Lie algebra, semi-direct product with our favorite module for that Lie algebra. This is not the case. Right? This is not a Lie algebra. It's a Leibniz algebra. Alright, so let's go to the quantum board. Oh, no, before I go to the quantum board, let me give the example that we care about, Poisson vertex algebras, that is going to be generated by that in some sense. So an example of a Poisson vertex algebra, the most trivial example, is the Poisson vertex algebra generated by two guys, beta and lambda and gamma. So this is called, this is the beta gamma system, and this is as simple as this. Okay, so gamma beta is equal to -1. And the Poisson vertex algebra as a vector space, what is my P? It's just the symmetric algebra on the whole space, which is K delta, spanned by beta and gamma. So this means, well, probably this is too bad for notation. There's a twist by I'm putting here something that is non-linear. Here I should have written down a central element that then kills that central element. Remember how I did all the affine algebra and the Virasoro algebra? The center was an element of the Lie algebra. It can't be a number. This can't be an element of the field. My bracket was a map from G tensor G into polynomials with coefficients in G. And now suddenly I'm writing a number. So write a central element, take the symmetric algebra, divide by the idea such that that central element is 1. Okay? From now on, my centers are going to be numbers, and I'll forget about keeping a universal central extension. All right. So, but one thing that I want to mention here is that this is a remember this is a commutative, associative algebra. And this is why this beta was the generator of a module for the algebra of functions by gamma. So this is going to change now in the quantum world, and things are going to get complicated. So now I want to define what a vertex algebra is. Definition. A vertex algebra is, but I mean, it sounds scary when I write this, but it's really, the only thing I'm going to do is, I started from the Poisson algebra, usual definition, and I changed to you what the axioms of a Lie algebra were. Now I'm going to change for you what the axioms of a commutative algebra are. So the only thing I'm going to deform is a commutative product. So the Lie bracket is going to be the same. So a vertex algebra is a K of del module. Oops. K of del module V, just instead of G, with, first of all, an operation, just as in the usual case. Now I'm going to write brackets instead of braces, just as before. So this is a Lie conformal algebra, or definition of Lie algebras. And now I want to tell you what a commutative associative product is and the Leibniz rule. But it's really just a deformation of the usual notion of Poisson algebra. So an operation, which is the product, and a unit. So okay, what are the actions? And a unit. Probably the unit might want to write it like this sometimes. So what are the actions? This wants to be a commutative associative product. First of all, the unit is a unit. So 1 times A times 1 is equal to A, and A lambda 1 is equal to 1, lambda A is equal to 0, which is what you would expect of the units of the universal enveloping algebra for Lie algebra. But now, so this is the trivial axiom, but now let's deform the commutative product. The product is not going to be commutative. It's going to be A times B minus B times A. This is no longer 0. This is going to be the following. You compute this lambda bracket. This is a polynomial in lambda. You integrate that polynomial. Integrate that polynomial. We've got a polynomial in lambda again, with coefficients in B. And now apply the following limits to that guy. So now this is an element of V again. So this fails to be commutative, but if we put del to be 0, this is again commutative. And if you put lambda to be 0, this is again commutative. So I hope this expression is clear. So this wants to be like, if A lambda B was the sum of lambda to the n Cn, this here is the following. So if A lambda B is the sum lambda to the n Cn, the right hand side there is just the sum of what? Minus del to the n plus 1 over n plus 1 applied to A, to Cn. Okay? I integrate and I put, oh, there's an overall minus. Oops, no, I'm missing 0. I'm missing the, well, the one limit is 0 and I'm integrating, so that's good. There's no constant there. Okay? Alright, so that's the non-commutative part, but now the problem is that it's also non-associative. So the associativity is slightly harder. So the day you're commutativity, you should really think, I'm going to write a bunch of actions that you will forget. But what I want you to remember is the following. A vertex algebra is a Poisson algebra with this funny Lie algebra structure that we had, that was very natural. And now I'm just writing deformations to that. And small deformations, in the sense that they're all up to constant total derivatives. So in the loop space, when you write this integral symbol, you're going to miss these guys. All right, so let's write that as a fifth condition. A, B, C, faster. A, B, C minus A, B, C. This is also something that you can write in terms of integrals, and so I'll do so. So you do the following: you take the lambda bracket of B with C. This is a polynomial in lambda. People don't like this term, but okay. So you integrate this guy with respect to lambda. You are going to apply the symbols 0 to del, but instead of applying this to the result of this lambda bracket, you will apply it to A. So this del is going to be applied to A. And then you do the same thing for B and C. Let me write this explicitly. I'll do examples of this, and then we switch D and A. For those of you who know a little bit about algebras that are non-associative, but the associator is symmetric in A and B, it's natural that this is going to lead to a Lie algebra. So when you learn the first time how to get Lie algebra from an associative algebra, you write down the commutator and you get a Lie algebra. You don't really need the commutator of the algebra to be associative. An algebra such that the associator is symmetric. This is called a left symmetric algebra, if I didn't get this wrong. Then the commutator, it's a Lie bracket, satisfies the Jacobian condition.
For physicists, you can tell that this is just normal ordering products, right?
For physicists, yeah, so for physicists, this product is a normal ordering product. So this product is a normal order product, and these are the problems that you have when you choose, you're going to write expressions like this, which are, this is not the same as alpha. This I'll do this very example in a second. So the way you choose how to put the columns in an expression like this depends. So I'll do this in a second. Okay, so let me tell you what this associativity property is in that example. So the example of the three bosons. So one example is the three bosons. So this is something that is generated by one guy whose lambda bracket in itself is lambda. Remember, in your language, you would write this as alpha z dot. So I'm going to start to connect this with the kind of computations that you do. I hate these z and w's. I want to make the point that you don't need them. But this corresponds to this in your language. Or if you wish, the commutator of this with this is one derivative of the delta function. This is why the lambda appears to the power 1. Alright, so let's look at this guy and let's compute that. Alpha minus alpha alpha. It can be such that this is generated by one guy and is non-associative already. Okay, so I need to compute alpha with alpha. That gives me a lambda. I integrate that out. It gives me a lambda square over 2. And I apply this limit. I get del square over 2. So this is just del square alpha over 2. But then I have the other term when I switch alpha with alpha. Okay, and I see that this alpha is already non-associative. So what is the problem in our geometric point of view? Well, before I get there, let me give you the example and complete the square so that it becomes at least clear in one example the difference between the four corners of the square that I started last time. So theorem, let G be a Lie conformal algebra or Lie star algebra. There exists a unique U of G vertex algebra such that this embedding is a morphism of Lie algebras. I mean, how do you define what the universal enveloping algebra of a Lie algebra is? You choose that condition. And every other vertex algebra comes with a morphism from it. So the G inside of here is a Lie algebra morphism. and is universal with this property. Alright? So I want to give you this in one example so that it becomes very, very clear. So, okay. So let's start with probably, okay. Yeah, so it's a bad idea that I use this notation because now I'm going to go to finite dimension. So let's write this, instead of G, I'll write this V, ouch, V, Vm. Okay, so example. And this is going to clarify everything at home. So let's start with G, our finite dimensional Lie algebra. Non-degenerate bilinear form. Think on the Killing form. Symmetric, invariant bilinear form. And let's form our current algebra. So I want to describe you what is the vector space at least, and soon I'll tell you what is the vertex algebra structure in that vector space. But as vector spaces, the universal enveloping algebra of that algebra looks as follows. So here, remember what the bracket was. The bracket was A lambda B is equal to the bracket of AB plus lambda times the pairing. And now we'll divide by the ideal where this K is going to become a number. K is probably by ideal, L, but I'll put the level, and I'll put this L there. So I want to describe you how that guy behaves as a vector space. How is this guy a vector space? So step one, attach to this conformal algebra a non-ST Lie algebra. This Lie algebra is G hat, which is the application algebra. The brackets here are normal brackets. So I'm not sure how people are used to writing these brackets. I'll write them like this. So this is A, B, tensor F times G, plus the pairing of A and B times the integral of F dg. So if you're not used to this one, then we just write this in a different way. AM BN is equal to AB n plus n plus delta n minus n. Perhaps I need an m there. This is the problem that I never remember this. And then the pairing of AB times the center. Yeah, but the center I'm gonna. Yeah, I want to the algebra. That's right. So here AM means AM is equal to A times D to the n. So we have this Lie algebra, so that's step one. Step two, identify a subalgebra of that. Actually, this I could do much faster because these are the kind of things that you are used to do, I think. So step two, I'll look at this subalgebra inside. So positive power series in T. So I'll call this G plus. Probably G hat plus if you wish. And step three, let's form the induced module. Let's form the Fock module at level L for the Lie algebra G, or G hat if you wish, which is the induced module from G hat plus to the whole Lie algebra from the one-dimensional representation. In this space, what happens? All of this guy acts as 0, and this guy acts by multiplication by L, the level. So that gives me a vector space, and this vector space is this vertex algebra. I'm going to tell you what is the structure of the vertex algebra in that vector space. I can't tell you right now what is the product and what is the lambda bracket, but I'll tell you in a second. But this is enough for me to describe the square. Yeah.
Vector space, isn't it just UG minus?
As vector spaces is UG minus, that's correct. But then in that vector space is much harder to describe the product. But you see, the thing is, the point to make is that it's a quotient of the universal enveloping algebra. It's not that passing from the bottom row of our square to infinite dimensional loop spaces was just taking loop spaces and taking universal enveloping algebras. So let's look at our square in Poisson vertex algebras and in Poisson algebras. We started from our data, which is G is finite dimensional. What did we get here? This was simply sim G. This is a Poisson algebra. What did we get here? This was simply sim Cour G, or sim of K of del of G. What did we get now on the vertex algebra side? We have this UL of Cour G, which is, as vector space, is a Fock module for that infinite dimensional Lie algebra. Fock L of G hat. Notice that this is not sim of G hat. Cour G are just polynomials in a variable with values in G. So this is sort of like sim of the G plus. And down here we have the universal enveloping algebra of G. This is a deformation of this, and this is a deformation of this. I provided to you a functor in this direction that I call zoo. I won't provide you a functor in this direction that is also called zoo. That's slightly more complicated. But this is a commutative diagram, where this is what you should keep in mind when people talk about vertex algebras. The finite dimensional picture is just symmetric algebra of a Lie algebra. The deformation of this is its universal enveloping algebra. The vertex algebra lives here, and the Poisson vertex algebra is a symmetric algebra. So this should be the picture that everyone should have in mind. And I want to do the same when instead of G here, I'm going to put the cotangent bundle to a Poisson to a manifold. So that's the whole point. I want to do this when I replace G by the cotangent bundle of a manifold. Or the tangent bundle, perhaps, of a manifold. Alright, so what is the complication? So I want to tell you in which sense vertex algebra is quantized Poisson vertex algebra. So definition, a filtration Fi inside of Fi plus 1. Subspaces, all of them inside of a vertex algebra P, such that Fi, Fj live inside of Fi plus j. And now the bracket, well, the derivative of Fi sits inside of Fi plus 1. And now remember how I defined the grading for the brackets. I'll take A lambda B with the sum of lambda n Cn, and I'll require that Cn lives inside of Fi plus j minus n minus 1 or 2, I think 1. And here, this guy is in Fi. This guy is in Fi infinity. So I'll say that that filtration is compatible with the vertex algebra structure. Notice that I can't talk, since my algebra is no longer commutative, I can't talk of gradations. I have to talk of filtrations now. So, if that situation happens, if I have such a filtration, then P, which is the sum over K bigger or equal than 0, oh yeah, let's suppose that this starts at 0. Of Fi plus 1 divided by Fi, this is a Poisson vertex algebra. Oh no. I think I did this. Let's try to fix this 2 in a second. So how does this work? I take A times B minus B times A. The only thing I need to remember is that I want to get in the associated grade the commutative product. So I look at A times B minus B times A. By this axiom here, this lives in Fi plus J. Right? If I take A and B in Fi and Fj, the difference, what is this? It's an integral of this lambda bracket. The integral is going to raise by 1 the degree. Right? So it's going to land in I plus J minus 1 at the most. So it's going to be 0 in the quotient. Okay? So this is a Poisson vertex algebra. And in that sense, if I take the associated Poisson vertex algebra to this universal enveloping algebra G, I get the symmetric algebra of that. Okay, so let's try to set up the actual problem we want to solve now. Out of geometric data, out of a current algebra, I should have mentioned something for Damian's talk. Wow. Out of a current algebra, we constructed a Poisson vertex algebra P of E. Remember how this was done? This was very, very simple. In degree 0 we have functions, in degree 1 we have our current algebra, and the lambda bracket was declared to be A lambda B, just AB plus lambda times the parent, AB. So this gave me a Poisson vertex algebra. The question is, does there exist a vertex algebra that quantizes this? Can I quantize this? And if so, is there any complication? So this is a very natural statement, in as much as the previous version, the finite dimensional version, was also a good question. If I give you a Poisson algebra, right, a Lie algebroid, can you quantize it? Can you produce me an associative algebra that deforms this algebra functions of the Lie algebroid? So what is the complication that we may find here? It's not the non-commutativity. The biggest problem is the non-associativity. The biggest problem is as follows. Let's take the simplest of examples. Let's take the example where E is just Px plus P star x. That's the very simplest example. And we have always just functions. Okay? So let's say our manifold X has a coordinate gamma. So we will have our gamma that lives in OX. And let's say we have a vector field, d by d gamma, that I will call beta. So this lambda bracket of something in P1 with something in P0, remember what it was? It was beta lambda gamma is equal to 1, because it's the vector field acting on the function. So at the very least, any quantization should have these two guys, gamma and beta, for a vector field and a coordinate. But now we realize the following. If I take gamma times beta minus gamma times beta, the associativity property tells me, well, I should compute the lambda bracket of these two guys. I get 1, I integrate that guy, and I apply it to this guy, and I get del gamma times 2. The same thing happens from here, switching gamma with gamma. So whatever I do, I'm not going to be able to describe it naturally in geometric terms. Because whatever I get, the object that I will associate to beta cannot live in a module for the ring of functions. It's not going to be a module for the ring of functions because it's not an associative product. This is the failure of this beta to be behaving nicely as a module over functions. Right? So if I want to give you a vertex algebra, I will start by saying, okay, so F0, there's no choice. F0 is going to have to be OX, or some deformation of OX if you wish. But as a vector space, it should be OX. And F1 somehow should want to be like OX plus something else. And this something else cannot be a module over OX. So I'm outside of geometry in the usual sense. And the way of quantizing this Poisson vertex algebra in particular happens to be that there's not canonical quantization, there's a gerb of them, and this is a complicated problem that I don't want to talk about. But I want to tell you how to solve that problem. Okay, so this is the problem we want to solve. But now, before doing that, this I'll do in the next talk. Before doing that, I want to bore you. I want to bore you relating what vertex algebras are, the way I presented them. I'll make 25 minutes. So I'll go back to the definition of vertex algebra and I'll relate this with the definition you know. And I'll bore you by doing a computation, which is the Sugawara construction, with something you know, but I told you that I want to tell you how to compute things with the lambda bracket. So this is what I will do now. So the way that you are used to seeing vertex algebra is as follows. I define the vertex algebra with only two operations. A lambda b and the operation A times b. So the way people typically define vertex algebras is as follows. Is they say, well, you give me a vector in a vector, so definition. A vertex algebra is the data of a vector space V and an operation from V tensor V. So this is a physical definition of a vertex algebra into Laurent power series with coefficients in V. And people typically write this operation as A box B mapping into the field associated to B to A applied to B. So this is the normal way of writing what a vertex operator algebra is. So this mapping from A to Y of AZ is called the state field correspondent. And notice, so this A is a vector that lives in V, and this Y of AZ is a guy that you feed in vectors in V and it gives you a Laurent power series with coefficients in V. So these guys act on V, and these guys are elements in V.
So what should you write in the morphisms? So V for whole power of Z.
Sorry?
In the morphisms. V.
So this Y of AZ lives
In the morphisms of V, right?
yeah, so let me write this. Y of AZ lives inside of home from V into Laurent power series in Z. But the definition of Y of AZ requires, it's coming from this one. So, okay, so how do I relate? No, I need to give you the axioms. So the axioms are as follows. So the only important axiom is locality. This is as follows, that if you grab the field that corresponds to 1A, and you grab the field that corresponds to another B, then if you put Z and W at different points, this thing should be 0. So I'll translate this into Z minus W to the N is 0 if N is big enough. I can certainly not ask the commutator to be 0, but I can ask it to be 0 after I multiply by Z minus W to some high power. And the second axiom is translation invariance. This is that, I won't define this, okay, so I should. Let me write another axiom, which is if you grab Y of A, Z, and apply it to the vacuum, this thing, first of all, doesn't have any pole. A priori, this would have a pole in Z. So first of all, this doesn't have any pole, and it looks like this. It looks like this. I'll define this as del A Z plus something of the order of Z squared. So the content of this line is that if you apply any field to the vacuum, you don't get any singularity. The first term is your original state, and the second term is defining it. This defines this operation. And I obtain the del of Reimundo, K of del mod. Notice therefore that any state determines a field, and by that procedure, the field determines a state. And now with something that you do. Okay, so finally, what is the last axiom is that, let me write it here, 3. With that definition of del, I can do this. I can take del and commute it with y of AC. This is translation invariance. And this is d by dz of y of A. So these are the 3 axioms. And the 2 definitions are related as follows. If you give me these guys, like this, I will do the following. I will define, how do I want to define this? Okay, so let's do this. Let's write y of AZ, B. Let's write this thing as what? As A, N, B, Z to the minus 1 minus N. Notice that for n large enough, that thing is 0. That was the condition of landing on a Lorentz power series. So from the old definition to the new definition. So A minus 1 B is AB in the old definition. And the sum of A J B lambda to the J divided by J factorial, J is positive. This is the lambda bracket in the old definition. And A minus N B, well, probably minus A B. This is the derivative J times, or plus 1. And J times of A times B in the previous definition. So this relates the 2 definitions. In other words, the minus 1 product, or the normally ordered product, and the positive product determine the whole structure. So let me give you one more piece of dictionary between what you were on this lambda bracket formalism, is that once I define this way, then I can take commutator. And I can look at the commutators of y of AZ with y of BW. No, let me just do something different than this. Yeah, I don't want to see lambda delta functions. Let me write this. I think you're more used to this notation. Y of AZ dot y of BW. And you say this guy is regular. This is a regular part that you define to be the regularization procedure. So you define this guy to be the regular part of the product of 2 fields, plus the singular part. And what is the singular part? Well, this is some field that corresponds to some C0 field of W over Z minus W, plus, let me call this C1, no, I want to call this C0, plus some field that you would associate to another state, C1 of W over Z minus W squared. Plus, and this sum is finite. So when you see an expression like this in physics, I will translate this by saying, this guy here is the field that I would associate to A times B in my formalism. And all of this series of the singular parts of the OP, I would write this as C0 plus C1 times lambda plus C2 times lambda squared, and so forth. And I know this sum is finite. And from now on, I'll forget completely about Z, W, singular and non-singular. The only thing I need is this polynomial and this operation. So let me give you an example of why this is powerful.
It's normal order product still depends on 2 variables. You said the equal.
Oh yes, I'm sorry. Yes, you're right. Yes, I need to be careful. I'm being careful. This depends on 2 variables. The way we write this is a different thing. I will take the commutator of these 2 fields, and you will get this series, replace Z minus W, 1 over Z minus W here by the delta function on Z minus W. So to properly relate the 2 things, I should do this. So the formal statement is this, is y of AZ bracket with y of W This way I kill the regular part. And this is just a sum of y of Cn of W times the derivative n times of the delta function of z. And this is the lambda bracket in the other format. So this would be explicitly translated to a lambda b is equal to the sum of Cn lambda to the n. And this lambda to the n is measuring how many derivatives of the delta function you have. Yeah, that's a good observation. I haven't thought. Okay, so let me do a computation. So I'll bore you with a computation, and then I'll go back to quantization in the next lecture. I'll go back to actual geometry in the next lecture. But the whole point is that this formalism, I want to sell it as something that you should be looking at when you're doing computation on endpoint functions. So remember how the Virasoro algebra was, or the Virasoro conformal algebra was? It was only this. And remember what the affine Katsumudi algebra was? This was only this. Okay, so the Segal-Tsukuwara construction is as follows. Certainly there's no morphism of Lie algebras from this into this. But what is interesting is there's a morphism of vertex algebras. From the vertex algebra associated, the universal enveloping vertex algebra associated to Virasoro sits inside of the universal enveloping vertex algebra of the affine algebra G hat. So this is a statement that you can prove in physics by just writing down the operators, and it takes a long computation to prove that statement. It is a statement that you might have done, most of you have done, the computation of writing down the ln's, lm, and the commutator of those guys. So let's do that computation once more. But my point is that at no point I need to write the ln's, nor lm's, nor the z's, nor the w's and get this result. So let's do this. So let's pick a basis AI and AJ orthonormal for our pair. And let's write down, let's suppose our Lie algebra G is simple. So that the Casimir element on the Lie algebra is just AI. This is just a Casimir. And if our Lie algebra is simple, semi-simple, the thing is that I want this. Let's fix simple, so that this guy acts, the adjoint action is a reducible representation, this acts by a number. And I'll call this number 2a check. This is the eigenvalue by which this operator acts on G in the adjoint representation. Okay, so let's write down this L. Oh no, probably it's a bad idea. Yeah, no, I'll write it there anyways. As 1 over. No, let's fix that notation later. Let's write L tilde, the sum of AI. I'll start writing repeated indices. Let's just sum them. This is now an element. This times is in the universal enveloping algebra of G. So this is the statement. If you grab the Casimir element, and remember this because in the geometric setting this is going to be much more complicated. If you write the Casimir element for the finite dimensional Lie algebra, which is an invariant, in the infinite dimensional world, it's the same expression, and it's going to give you Virasoro. So let's prove that. Let's take the lambda bracket of a current B, let's say A, lambda L tilde. Oops.
You wrote twice the same thing?
Sorry?
You wrote twice the same thing, what does it mean?
Oh, it's just that I'm forgetting this symbol. I don't want to, I want to be a physicist and sum over repeated integers. I need to apologize and I need to blame Lazaro. You should have known this. I'm forgetting Leibniz. So add a few lines back when I defined you what a vertex algebra was. No one complained that I didn't define you. I told you how to define the product. I didn't tell you how to define lines. That's the most important tool, and this is something that you guys use, which is the non-commutative weak formula, which is the lambda bracket of A, B, and C. I should have explained this before, I'm sorry. But now we'll use it. The lambda bracket of A with B and C, before it was this, A lambda B times C plus, so let me write that as a minus B A lambda C. So before this was 0, that's a Leibniz rule. Now it's no longer 0, it's also an integral. So that's a weak formula in your language. That's a non-commutative version of it. Okay, so let's do this here. We have 10 minutes, well, 8 minutes. Let's do this quickly. A lambda L2. Okay? So I take AI times AI. So that's the lambda bracket with this guy plus A times AI times lambda. So that's just the bracket with the first guy. Plus AI times A upper plus AI upper I times lambda, and now we're missing the integral term. So this integral term, and it's computed, and it's what? It's the integral of the bracket of this with this AI. So this is AI upper I plus lambda plus gamma A upper. I just computed the lambda bracket of this term with this term. It's a bracket plus a period. The gamma. So let's do the computation. Alright, so these two terms are easy to see. Okay? These were orthonormal bases. What did I do wrong? I'm missing in the first term is K, the pairing of A with AI, and I'm missing the multiplication by A upper I. So this and this term here, and I'm missing here the K, and here the K as well, of course. This term and this term here, what are? So I have a sum of the against one basis times the dual basis, and the same here. So this thing is just 2 times lambda K times the vector A, and I got rid of these 2 terms. Okay? Now I claim that the invariance of the form makes these guys be 1 minus the other. So exercise. Check that in G squared, these 2 things kill each other. But let's start with the integral term, which is a little bit better. What is this guy here? Right? So I'm going to put a minus here, to either act on the right or on the left. So put a minus and put AI bracket A, and then commute this guy with a minus, and write A upper I, adjoint action, A upper lower I, adjoint action on A. This is the action of the Casimir element on A. So this whole thing is a multiple of A, which is 2H check times A. So this integral here is going to put plus 2H check times lambda. Remember, this is from 0 to lambda, the integral. Lambda times A. And now I claim this is 0. Well, this is obviously 0. This is invariance of the Casimir. The Casimir does not depend on the dual basis. So if you switch the basis AI by this other 2, this should be equal, but on the hand there's a minus sign. So this is obviously 0. So the brackets on the Lie algebra, this guy is 0. So this guy disappears, and these 2 guys exercise show that on the square of a Lie algebra, these 2 guys are 1 minus the other. This is just invariance of the basis again. Or the invariance of the linear formula. So this is just 2k plus h check times A. So we'll define this.
2 lambda.
Oh, times lambda, thank you. So I'll define L to be 1 over 2 k plus h check the sum of AI, the Casimir element. I am assuming now that the level of the Lie algebra is not critical, so that K is not minus H check. Otherwise, everything's screwed up. And now what I realize is that L lambda A is equal to, well, I need to do this. I need to replace lambda by minus lambda minus del and put an overall minus. Remember, that was Q symmetry in my Lie algebra. So this is del plus lambda times A, which is in your language, currents are primary of conformal weight 1. So this means currents are primary of conformal weight 1. Primary means that there's no lambda positive terms there. There's no OP is higher, and conformal weight 1 is that there's a 1 in front of this lambda. So let's finish the computation. So I have L lambda A. So now I can do L lambda A times A. And it's again just an application of the Leibniz rule. Now this time it's even easier. But I want to show the cubic term of the Virasoro Lie. L lambda AI. And this is as simple as this. I want a 1 over 2K plus H check. So this is 1 over 2K plus H check. L lambda AI. L plus lambda AI times AI plus this plus AI L lambda AI prime, which is just del plus lambda a prime. And now I'm missing the integral term. What is the integral term? Is the bracket of this guy with this guy. So let's write down that integral term. 0 lambda, and now I need to be careful. Is this plus lambda AI gamma bracket with the AI prime? And now I close the braces. So let's finish. Let's see. I have a del AI, and now I have a plus I del AI. Del is a derivation. Therefore, these two terms with del just give me a del A lower I, A upper I. So this is just del being a derivation. The terms with lambda, now lambda is linear. I have lambda AI and lambda AI. So I have plus 2 lambda AI. And I got rid of this and this. I'm only interested in the integral term. So this is plus the integral term. So this is just del plus 2 lambda L plus the integral term. So let's compute the integral term. Okay. We have 1 minute. It should be almost enough. So what is the integral term? And I promise there's no more computations in the next talk, but I want to sell computations. So what is the integral term? I need to compute this lambda bracket, right? So I need from 0 to lambda, del plus lambda, A over I, gamma, A upper I, d gamma. This is, well, sesquilinearity tells me that this del here goes out as minus gamma out of the bracket. So this is 0 to lambda of lambda minus gamma, and now I need the bracket of AI gamma A upper I d gamma, which is the integral between 0 and lambda of lambda minus gamma, this bracket. This bracket is what? Is AI, A bracket with A upper I, that's 0, plus the pairing. And the pairing is gamma K, and the pairing with AI with A upper I, d gamma. So what is this? This guy here is just 1 for each I. So this is just the dimension of G. For each one of those guys, I define that basis to be dual. So that's just the dimension of G. And now I need to integrate this polynomial, which is lambda gamma plus minus gamma squared. So the integral of that guy between 0 and lambda is lambda cube over 3 minus lambda cube over 2, which is lambda cube over 12 times k times the dimension of g. So here I should put lambda cube over 12 times k dimension of g, but the only problem is that I have this guy floating around, 2k plus hs. So what did we prove? That there's an embedding of the Virasoro algebra with central charge k, the level of the Lie algebra, dimension of g divided by these two guys, in just 2 applications of the Leibniz rule. So this doesn't sound too illuminating, but the point is that if you do the same thing for the universal enveloping algebra, this will do it, I won't do it. But if you do the same thing for the universal enveloping algebra of the tangent bundle of a Calabi-Yau, you find explicitly the Virasoro of the right central charge on a Calabi-Yau manifold, which is something that requires a lot of computation if you want to do this on a curved manifold explicitly, but this language allows you to do this. Okay, so I won't do the computation, but I'll point out what does that mean in the next one.
Any questions for Reimundo? Anybody who did calculations? Yeah. So let's thank him again, and we meet 5 past 4.